All right, welcome everyone to the exam 2 review. Again, sorry we didn't quite get there in class, but these things happen, so it's fine. All right, so first thing first is we talked about the electric force. So again, electric force would be if I have two charged particles, one is Q1, the other one is Q2, separated by a center-to-center spatial distance of r. What the electric force, or Coulomb's law, says is that the electric force between the two of these is equal to K times the magnitude of Q1 times the magnitude of Q2 divided by the spatial separation distance squared, where K is equal to 1 over 4 pi epsilon naught, which is just a number. Again, this will be on the front page of the exam, so don't worry about writing that down. Again, this is a little more complicated than the electric force, or sorry, the gravitational force, because again, it depends on how the charges are related to each other, whether you get an attractive force or a repulsive force. So if we had, say, like charges, then this equals in a repulsive force. Where if we have unlike charges, then this is equal to an attractive force. So again, for example, if I had, say, a positive charge here and a positive charge here, this would then manifest itself as a repulsive force. So this would be the force on 1/2 in this direction, and this would be the force on 2/1, where the direction of the force is along the direction of the line that connects the two. But if instead I had, again, a positive charge here and say a negative charge here, then this is going to be an attractive force. So this guy's going to be attracted in this direction. So this would be F12 in this direction. And then this would be F21 in this direction, where again, this guy satisfies Newton's third law in that the forces are equal magnitude, but opposite in direction. So if I have more than two charges, we then have to use the superposition principle, which says that the force on the ith particle is simply equal to the sum over j, where j is not equal to I, of the force on the ith particle by the jth particle. So again, this is just a vector sum over all of the different individual forces between the pairs. So again, if I had, say, this is I and this is j and this is k, so the total force on him would then be the force on I from j plus the force on I from k, vector sum together, and then depending on if they're positive signs or negative signs or some mixtures. So again, this is what we call the superposition principle. So just the vector sum over all the possible forces. So that's pretty much it about that. And then from there, we moved on to the electric field. So for the electric field, we said that the electric field is defined as the limit as the charge goes to 0 of the electric force per unit charge. Again, this guy has units of newtons per coulomb, and as we later found, this also has units of volts per meter. But again, delta Q goes to 0 here does not mean that this is a derivative. What it means is that this has to be a test charge small enough that it doesn't change the charge configuration in which it is. So that when we watch how it moves and we map out how it actually moves, then it's not changing the charge configuration due to being too large of a force to move the charges around. So this is in general. So this is always going to be true. If I was dealing specifically with a point charge, then for point charges, we find in this case then is that the electric field of a point charge is equal to K times Q divided by the distance r squared. So this is the magnitude of the electric field. So this just means if this is my charge with the charge of Q, if this is my spatial separation, so from the center of this charge to the location of the point that I'm interested in, point P, then the electric field, as long as Q is positive, will then point radially away. But if the charge is negative, it will point radially inward. So it just says that the electric field points radially away in all different directions. So this is my electric fields, where the magnitude is given by the distance I am away from it. So again, points radially away if it is a positive charge, but points radially inward if it is a negative charge. So again, if I have more than one charge in my space and I want to know the electric field at some given point, again, we're going to use the superposition principle, which says that the electric field at any point P is simply equal to the sum over all of the individual electric fields at that given point. So here, I just represents the different charge that I'm looking at. The point P is the point in space that I'm interested in. And then the distances will be dependent on where the charge is located to that point of interest P. So that's the superposition principle again. And another electric field which is of use to us is for parallel plates. So the electric field for a parallel plate is equal to what, sigma over twice of epsilon naught, where again, sigma is the charge density. Technically surface charge density, which is equal to the charge per unit area. Again, this is the magnitude. And as we said in class, what happens is what if I had a sheet of charge, which is infinite in length, then my electric field here points perpendicular to the surface, either radially inward or radially outward, depending on the sign of the charge. So in this case, if the charge is positive, it points radially outward. But if the charge is negative, it's going to point radially inward. So these are our electric fields of use, which means that if I had a parallel plate capacitor, I have two basically sheets of charge. One is positive, one is negative. As we again discussed in class, the electric field on the outside will be 0, and the total electric field on the inside will simply be twice of this guy. So for a parallel plate, unit here, this is my parallel plate, my two plates. So this is positive charge, this is negative charge. My electric field on the exterior will be equal to 0 on both top and bottom, but the total electric field on the inside will simply be sigma over epsilon naught. So this will be the magnitude of the electric field, where an electric field always points from the positive charge to the negative charge. Okay, so that's that. The last thing we talked about was this works both ways. So what this says is if we know the force, we can then find the electric field by simply plugging out or plucking out the charge at that particular point to then find the electric field at that particular point. But conversely, what this says is if I know the electric field at any point, I can then find the force by simply multiplying by the charge. So this says that the force then is also equal to the charge times the electric field at any point in space. So we looked at a lot of different situations of this, mostly for electrons and things flying through parallel plates, watching the deviation for these. But again, if I was looking at a situation like that, so this is plate Q, this is plate, say, minus Q, and I have a charge moving on the inside. Let's say this is positive charge. Again, my electric field will point from the positive to the negative. So this would be the direction of my electric field. In this case, since the charge is positive, when it moves inside of the plates, the force will then be in the same direction as that of the electric field, which means that in this case, the electric force would be downward in this direction. So overall, this particular particle would move in a projectile motion type pattern and do something like this. So this guy would be deflected by an amount of y. Great. So all of this was then chapter 16. So all of this was chapter 16. We talked about some other things too, like the electric fields inside of capacitors and all that kind of good stuff. But again, those were mostly more concepts. And the very last thing we ended up with was dipoles. So we had an electric dipole. So the electric dipole, we have the electric dipole moment is equal to the charge of the positive charge times the distance between the two, written as a vector. So that just means that what if this is my negative charge, this is my positive charge, where these two have the same magnitude of charge, just opposite sign, separated by a spatial distance of d, then the d vector is the vector which points from the negative charge to the positive charge. So this is my d vector, where the magnitude of this vector is simply equal to the distance between the two, which means the dipole moment then points from the negative charge to the positive charge. So this is my dipole moment. again, this is opposite to that of the electric field, where the electric field points from the positive charge to the negative charge. The dipole moment points from the negative charge to the positive charge. With a dipole, we did things like put it in an external electric field. What we found is that the torque on the dipole, so the electric torque on the dipole is equal to the dipole moment crossed by the external electric field, which means that the magnitude of the torque is then equal to the magnitude of the moment times the magnitude of the electric field times sine of the angle between the two. So again, this angle here is specifically the angle between the electric field and the dipole moment. So again, if my electric field, say, points in this direction, draw a couple electric field lines here, and then my dipole moment points, say, something like this. This is my dipole moment. Then the angle here is specifically the angle between these two guys. So between the moment and the electric field. So this is the torque. And then this also has a potential energy associated with it. So potential energy. And we found that the potential energy is equal to negative the dipole moment dotted by the electric field, which means this is equal to negative of the magnitude of the moment times the magnitude of the electric field times cosine of the angle between the two. So again, this specific angle here, so the angle between the dipole moments and the electric field. So good. So those are dipole stuff. Great. So here's my dipole, and everything else here is electric. Good. So today we just finished off chapter 17. So let's talk about chapter 17. So chapter 17, we started looking at the fact that the electric field is conservative for us, which means we can define a work from there, which means, well, a path independent work, which means that we can define a potential energy. So again, we know that the work is equal to the charge times the electric field times the displacement times cosine of the angle between the two. Again, here I'm assuming that the electric field is equal to a constant. So this has no spatial dependence to it at all, like the parallel plate capacitor, unlike that of the point charge, which is then equal to negative of the change in potential energy. Okay. Now again, if this is not true, that it's a constant electric field, we would actually have to integrate, but since this is an algebra-based class and we don't actually integrate, so we don't have to worry about that. But just note that this is only true in this particular case. From here, we can then also define a new quantity, which says that the potential energy is the same thing as the charge times what's known as the electrostatic potential. So this is also equal to negative of the charge times then the change in electrostatic potential. So from here, this tells us then that the change in electrostatic potential is equal to negative of the electric field times the displacement times cosine and angle between the two, or the electric field magnitude is then equal to negative of the change of potential divided by the displacement in that particular direction. So this would be the x component, for example, of the electric field. So from here, what this says then is we can now look at things like conservation of energy. So conservation of energy says that when we're dealing with electrostatic potentials, we have the change in kinetic energy plus the charge times the change in the electrostatic potential is equal to the work done by the non-conservative force. But typically for us, the work done by the non-conservative force will be zero because we're going to ignore air resistance and all that kind of good stuff. So this now becomes conservation of energy. And again, let's go back here for a second. This here is the relationship between V and E. So again, these guys are intimately related, but again, the reason we use V a lot more than we use E is because this guy is easy to measure. It's a scalar, and it is so related to the electric field that it just makes it much easier to actually deal with, since it's both a scalar and it's easy to measure by using a voltmeter. Great. So that's mostly what we saw a lot. And then from here, using this definition, we can then look specifically at the potential of a point charge. So let's look at the point charge. So the potential of a point charge, V, is equal to K times Q divided by R. So if this is my charge Q, and again, this is my point R, which is some distance R away from the center of that charge, then this is the potential. Now, again, this is technically actually a voltage, which means that it's a potential difference, where the potential difference is related to a point way out here at spatial infinity, where the potential is actually equal to 0. So technically, this is the potential difference between infinity and this point R. So that's actually what this thing is measuring. So it's measuring the potential difference between these 2 points. So this is what this potential actually refers to. So here, again, there's no absolute value signs on the potential. Reason for that is that the potential does depend on the sign of the charge, unlike the electric field, which the direction of the field depends on the sign of the charge. But for the potential, it depends on the sign of the charge, not for direction, but for it being positive or negative. So again, potential could be positive or negative, depending on that sign of the charge. Again, if I have more than one point charge, and if I want to know what is the potential at some point in space due to a whole bunch of different point charges, again, this is just going to be the superposition principle, which says that the total potential at a point P is simply equal to the sum of all the individual potentials at that particular point. So again, I is just summing over the charge, and then P is the actual point of interest at what it is that I'm looking at. Good. So now going back to conservation of energy here, if I know that I'm dealing with point charges, then delta V I can determine from the actual potential from the point charges. Otherwise, this would just be something that I can actually easily calculate, or I'd have to be told what it is. Good. So that's pretty much all we did on that. And then after that, we looked at capacitors. So again, a capacitor is 2 conductors, which are areas A and separated by a spatial distance of D. And these guys are going to be attached to a battery, where as long as the only thing attached to it is the capacitor, then the potential across the plates of the capacitor will be the same as that of the battery. Again, the point of the capacitor is to store energy via the work that the battery does to supply charges onto the capacitor plates. So this one will end up with a maximum charge of Q. This one will have a charge of negative Q. So this one becomes positively charged. This one becomes negatively charged with the same amount. So every time I have to put a charge onto the plates, I have to overcome this Coulomb repulsion between the charge I'm trying to put onto the plate and the charge that already exists onto the plates, which means I have to do work by the battery. So in this case, the potential energy which is stored is equal to the work done by the battery, which is then equal to one of 3 things. So it's either 1/2 the charge times the potential across the plates, or it's 1/2 the capacitance times the potential across the plate squared, or it's 1/2 the charge on the plates squared divided by the capacitance, where again, this charge is simply the charge from the positive plates. Since the charge on the negative plate is the same, it's just opposite in sign. So this is the energy which is stored. The charge, which is actually stored on the plates, is simply equal to the capacitance of the capacitor times the potential across the plates. So in this case, if here are my parallel plates, I have a potential difference across the plates of V. I have a charge Q on here. Then plotting the charge versus the potential simply gives me a straight line, where that straight line is what we call the capacitance. So according to this definition, then the capacitance of the capacitor is simply the charge divided by the potential. Now, again, for a non-simple geometry, this is something which we'd have to experimentally measure. If it was a simple geometry, we could easily calculate this because we can calculate the potential difference across the plates. So in a specific case that we looked at, we found that the capacitance for the parallel plate capacitor was epsilon naught times the area divided by the distance. So this is only true for parallel plates capacitor. So going back to the energy, so for the energy, we can also store what's known as, or find what's also known as the energy density, which says that this is equal to the potential energy per unit volume, which is then equal to 1/2 of epsilon naught times the electric field squared. So basically the energy which is stored in different quantities according to each one of these. So this one says that the energy is stored within inside of the charge. This one says that the energy is stored within inside of the voltage or the potential inside of the plates. This one says that the energy is stored in both the charge and the potential, where this says that the energy is actually stored within inside of the electric field itself. Okay. So whichever way that you want to look at it, the capacitor stores energy again for later use. So these are our capacitors. Again, the point of the capacitor is to store energy. We store that for later usage, which we'll see more in the next section. We'll start looking at circuits. So we'll start storing energy across capacitors and circuits. And again, this one says that if I want to change the capacitance of a capacitor, I have to change its geometry. As I either have to change the area or I have to change the distance. But an alternative way that we can actually change the capacitance is to use what's known as a dielectric. So again, a dielectric is simply an insulator, where that insulator is put inside of a inside of a capacitor to increase the capacitance of the capacitor. So the way that this works is that the capacitance increases from the initial capacitance by an amount of this dielectric constant, where, again, as we talked about today, the dielectric constant is simply the ratio of the breakdown potential of the insulator to that of the breakdown potential of air. So the overall effect that this has onto the capacitor will depend on how it's inserted into the capacitor. So we talked about today, if we connect that capacitor to a battery and insert the dielectric, in this case, the potential difference stays the same. The reason for that is it's dictated by the battery. The charge will then increase because the electric field changes as well, because the electric field is going to decrease. So this becomes the charge increases. This also changes the potential energy, where the potential energy also increases. Now, if I disconnect it from the battery and then insert the dielectric, in that case, what happens is that the charge stays the same. So nothing happens to the charge, but the potential then decreases by a factor of the amount of the dielectric constant, and the potential energy also decreases by an amount of the dielectric constant. So these are our capacitors. So good. So let's talk about what type of problems to look at. So first, let's start off with long problems. So basically, things with capacitors would be a long problem. So kind of like the problem we looked at today, or the one that was in the group assignment today, where we added dielectrics or took them out or changed the geometry, and then we asked things about the work and et cetera. So that would be one nice kind of good long problem. It mixes a lot of these things together. Another long problem would basically be involving this type of stuff here. So this would be, say, long problem number 2. So in this case, you're looking at, again, you'd have to know the electric field, where that electric field can involve these types of electric fields here using superpositions, or the electric field from a sheet of charge, or this one here, which is the electric field from a parallel plate. And then look at things like deflections using Newton's second law, which again, just to remind us, Newton's second law says that the sum of the forces acting on an object is equally equal to the mass times the acceleration. So here, if I know the electric field and I know the charge, I can then find the acceleration. So these would basically be the long type problems. This one, note, would also involve things with potentials as well. So things with this would also be part of, say, long problem number 2. Things like conservation of energy, relationship between the electric field. And again, note that, as we mentioned in class, the high potential region is the positively charged plates. So if I had a positively charged plate, this would be the high potential region. And my negative plate, which is over here, would be the low potential region. So these would be things that you'd be responsible for knowing. And then basically everything else would kind of fall into the short answer kind of category. So short answer questions would be things like given certain point charges, what is the total electric field at a particular point? So again, like superposition, also superposition for this guy, right? So again, if I give you a configuration of point charges, I can ask you what's the electric field at a particular point, what's the potential at a particular point, et cetera, et cetera, et cetera. Dipoles, this would also be a good short answer type question. Short answer. Things like that. Also things about, say, like static electricity, what's static electricity, also things like dielectrics, things like that. So that's it. So not too terribly amount of stuff on this particular exam. Again, this exam usually is a little bit worse when it comes to average than that of the first exam. Reason for that is because now you're dealing with things like fields, and now you're trying to get used to fields and trying to get used to understanding what those things actually are. Next exam, usually the average will go back up, so that's a good thing. But anyways, so yeah, so that's about it. Again, no constants, don't write any of the constants down, so you don't need to know like fundamental charge, what that is. That'll be on the front page. Mass of the electron or mass of the proton, or the values of K or epsilon naught or anything like that. Anything that's a constant will be given on the front page, or any constants that you need for a particular problem, like a specific K. In this case, the dielectric constant, all that would be given in the problem, or you'd have to solve for it. So, but yeah, anything that's a standard constant, again, don't worry about writing those down. So that's about it. So not too bad. So let me know if you have any questions, and yeah, I'll see you guys on Monday.